Okay, so
Okay.
good evening, everyone. Myself, Manoj Khadilkar, co-coordinator of this FDP, that is Faculty Development Program. Okay. It is my immense pleasure to introduce to you today's speaker, that is Dr. Raman Raghunath Bane, sir, who is currently work as a principal of the Yashwantrao Bhosle Institute of Technology, Sawantwadi. He is also coordinator of this faculty development program. His area of expertise are resource management in virtualized environment as well as artificial intelligence. Now, regarding his educational qualification, he completed his PhD in computer science and engineering from the prestigious National Institute of Technology, Karnataka, that is NITK Surathkal. He completed his Master of Engineering in Computer Science and Engineering from Walchand College of Engineering, Sangli. He has more than 20 years of teaching experience. He also received scholarships from the Government of India for his master's and PhD. He has published more than 30 articles and presentations at national and international conferences. He also served as a member of Technical Review Committee at various international conferences. Also, he received IEEE Travel Grant Award for attending the 35th IEEE conference at Las Vegas in USA. Okay. So in today's session, he will be a talk on recurrent neural network, that is RNNs, and sequence modeling. So I request Dr. Raman Bane sir to continue with this session. Thank you. Over to you, sir.
Thank you, Manoj sir. Just a minute, I will present my. Just you remove your sharing.
What, sir?
You remove, you have shared that file.
Okay, okay. Yes, sir. Done, sir.
Hope is it visible?
Yes, visible.
Okay. Thank you, and thank you for joining all the participants. So today we'll see the recurrent neural networks, RNN. My agenda is to explain what is sequence learning, what are sequence learning problems. Then we'll talk about what exactly the recurrent neural networks, how the training is done for the recurrent neural networks, that is backpropagation through time. Then some additional part that we'll see that is required to train RNN, that is selective read, selective write, and selective forget. And we'll see the long short-term memory, LSTM, in the case of RNN. So this is my this will be my short journey. So what are sequence learning problems? So just now we have seen the convolutional neural networks. And if you see the convolutional neural network, the size of the input, or if you take the feed-forward neural network or backpropagation neural network that we have seen up till now, so the size of the input is always fixed. That is not varying. But in some of the problems, your size of the input, so if you take the image size for the CNN, what are all the inputs? Suppose if it is 28 by 28, so all the inputs will be 28 by 28. If the 64 by 64, so all inputs will be 64 by 64. So input size is not varying here. Also, input length will not vary. So here in recurrent or in sequence type of problems, or where the data sequence is there, so you will get different sizes in the input. So that we have to handle. And so this is about the convolutional neural network, the 32 by 32 size. This is in the feed-forward network. So what to take examples? And suppose our input size is 2 here, 2 words we are inputting. So what to make example, what to vector conversion, and here input size is 2, input size is 6. Just a minute.
Hello, sir. You are not audible.
Okay. Sorry for that. So what I was talking about, the input size is fixed. If you take the convolutional neural network, if you take the feed-forward neural networks, the input size is fixed. Okay. So as input size is fixed, also the input is dependent on each other in the sequence. But in the case of CNN, the inputs are not dependent. So one input is not depending on the another input. Suppose the input is suppose Apple, then it will be classified as Apple. And if you are giving the next input as car, then it will be classified as car. Here, the inputs are not related, but if you see the sequence related problems, or if the data sequence if you take, then the data is or the inputs are related, and input size, one input size may differ from another input size. So this is the difference in between the data that we are giving as an input to convolutional neural network and recurrent neural networks. And therefore, the computations, the outputs, and the decisions of the two successive images are completely independent of each other here. So as I said, it is a car, and first one is Apple. So in many applications, input is not of fixed size, already discussed. Further, successive inputs may not independent of each other. And in given the first character D, suppose one example that we'll consider here. So predicting the next input. So as we texting in the WhatsApp chat or Google search engine, so automatically the next character will be predicted. So given the first character D, you want to predict the next character. Suppose if it is the word may be deep. So next character will be E, and so on. So this is one thing. So when your input is D, the output is E. The next input is E, the output should be, further output should be E. And the next input is E, the further output should be P. And the next input is P, at that time you have to stop. So this is the way you have to predict the next character. And this is a sequence problem. So, and first, the second or the output is depending on the input, and also the second input is depending on the first input, or the second output you can say is depending on its second input as well as the first input, and therefore here inputs are interrelated, or there is interconnection. And the representation here, the orange or the blue block or the green block, so here the blocks are actually the networks. So each and every block here is the network. It may be a neural network. It may be of any layer, you can say. So it is a network block, I can say. So these are known as sequence learning problems. So where we need to look at the sequence of inputs and produce the outputs. Each input corresponds to one time step. So each input is corresponding to one time step. So at every time step, we should get the output. So at every time step, depending upon the input, not only that input, but previous input as well, you should get the output at every time step. That is our requirement. So considering the task of predicting the part of speech tag, suppose this is the second example that I'm giving. So suppose the input is it visible to you properly? I think. Okay. So suppose it is predicting the speech of the part of speech tag prediction. So suppose example is man is a social animal. So man is noun, is verb, a is article. So this is what natural language processing does. And suppose social is adjective. So after adjective, the most possibility is that noun will come. So that means after social, there cannot be an article or there cannot be a verb coming. So this is what the relation exists in between the inputs, and therefore outputs are depending upon not only input at that time, but the inputs at the previous times as well. So thus, the current output depends on the current input as well as the previous inputs. So further, the size of the input is not fixed. So in this example, the words are 5, but you can have the sentence of 10 words, or you can have, while completing auto-completion task, word auto-completion task, that was the previous example, it may be of any length. Okay, so here input size is also not fixed. And one thing that you have to observe here, each network, that means here the boxes, that is orange box, blue box, and green box that I have represented here. So each network, that is a network actually, and each network is performing the same task. That means whatever the parameters are set, so all these parameters are set equally in these all networks. So all these networks are performing the same task. That is very important thing here. Sometimes our requirement is maybe we don't need output at every time step, but we need output at the end only. That means review. So suppose if you want to review some sentences, and at the end of the sentences, if you want to give the review, then at the end or at the last time step, you need the output, and at the other time steps, you don't care. So that sometimes that may be the requirement. So simply you don't care at every other time step, only at the last time step, you can give the output. So this is what the sequence related problem. So in such cases, so one more example, this is first sequence could be composed of or video, you can say, is a sequence. Video can be a sequence, and video is nothing but the frames are there, or the multiple images are there. So every frame is a image. So you can say this is a second. So it is a sequence of images that forms the video. So this is what at the end of the video. So after looking at the video, if you want to conclude what it is, so it is a Surya Namaskar. So the entire video is a Surya Namaskar, but you don't want to predict the things at the previous time step, only you need to predict here at the last time step. Okay, you can predict at any time step, and you can conclude there, but it cannot be only, suppose if you are not taking the inputs, as I told, the output is exactly related to all the previous inputs that you have fed. Okay, and if you are not considering all these, and if you are looking at only the input at the last and you are concluding on that, then it will be only Namaskar. It will not be a Surya Namaskar. So like that way. So what are recurrent neural networks? So we'll start with, so these are the different examples that can be where exactly recurrent neural networks can be applied. So how to model such tasks involving sequences? So where sequences are there, how to model this? So our wish list is account for dependence between inputs. So we need to, some ways, we need to account for the dependence in between the inputs. We need to account for the variable number of inputs. That is our next thing. And make sure that the function executed at each time step is the same, as I have explained. At every time step, the network is same. whatever functionality of the network is same. So make sure that the function executed at each time step is the same, and we'll focus on each of these to arrive at the model for dealing with the sequences. So these are the things that we have to make clear. So what is the function being executed at each time step? So this can be written as, so SI is, if you are looking at the middle blue box, okay, and this can be called as a state at time step t. So SI or time step I, SI can be a function. This can be a sigmoidal function. So if you want to write the function, what is SI, you can very easily write with the help of the input and the parameters, because the networks are having, what is neural network? Neural networks are having parameters. So this is a simple neural network function. So sigmoidal function is, or any activation function is applied, and U is the parameter, B is the bias parameter, and Xi is the input at time step I. So this becomes SI. So SI is calculated in the middle, or you can say it is a hidden layer. So orange is the input layer, blue is the hidden layer, and green is the output layer. So at the output layer, how you can write the equation for the output layer? So Yi can be any activation function or output function, and the weights are, or weight vector is V Si, that is input to that particular network, plus C. Okay, C is the bias at that particular network. So I is the timestamp. So since we want the same function to be executed at each time step, we would share the same network. Okay, and sharing the same network, that means what? Sharing the same parameters at each time step. That is very important thinking here. So these parameter sharing also ensures that the network becomes agnostic to the length of the input. So you can add x1, x2 up to many, as much you want. You can go up to xn. And therefore, this shows that as you are sharing the parameters, as you are sharing the same parameters, that means as you are using the same network at every time step, that input size is not dependent. So you can take the input of any size. At the first time, you can take the input of, suppose if it is, these are the words, you can take 10 words. Next time you can input 20 words, and so on. So since we are simply going to compute the same function at each time step, the number of time steps doesn't matter. So we just create a multiple copies of the network and execute them at each time step. So how do you compute the dependence between the inputs? So that is again the question, how you can
देतो नाही नाही तुला देतो ना.
Okay. So how do we account for the dependence between the inputs?
चालू राहील, तुला त्याने काय फरक पडतो?
लक्षात नसते 100 गोष्टी करायला. Just a minute, sir.
काय?
Okay. Fine. So accounting for that, how do we account dependency in between the inputs? So it is very simple. You can look in the diagram. That means first output should be dependent on, or the output at the first time step depends on the input at the first time step. Output at the second time step depends on the input at the two previous inputs, or it is depending on x1 and x2. Y3 is depending on x1, x2, x3, and y4 depends on x1, x2, x3, x4. Okay, so this is what the dependency. So, but let us first see, this is an infeasible way of doing. Why it is infeasible way of doing? Because what we have said that at each network, the same function should be used. But if you think of the function at y1, so y1, if you look at the function, is f1 is a function of x1, y2 is a function of x1 and x2, y3 is a function of x1, x2, x3, and the network is now sensitive to the length of the sequence. Okay, and that we don't want. And for example, a sequence of length 10 will have f1 to f10, whereas for a sequence of 100, we need f1 to f100. So that may be the problem. And therefore, the solution is add a recurrent connection to the network, and this is called as recurrent neural network. So this is in the diagram you're observing a recurrent neural network now. And at this particular time, the same network parameters are shared in between all the networks. So the blocks you considered as networks. So what are the how you can write the function for it? So SI, I already said SI is the state in between state at the hidden layer at time steps I. So it can be written with the sigmoidal function, with the parameters, with the input, and with the previous input as well, or in the with the previous state. So Xi is the input at the time step I, and Si minus 1 is the state in between state at time step I minus 1. And Yi is, you can very easily write Yi as output function of Si and the bias. Or you can also write the same function. Yi is equal to the function of Xi, Si minus 1, W, U, V, and the biases B and C. So Si is the state of the network at time step I. The parameters are W, U, V, C, and B, which are shared across time steps. And the same network can be used to compute all the outputs, that is Y1, Y2, up to maybe Yn, or up to, suppose there are 100, then up to Y100. Okay. And this is what the compact representation. So the same W is, as you have added the recurrent connection. So the same network can be represented. It is a short, or it is a compact representation of the same network. So let us revisit the sequence learning problems that we have. So initially we have not added the in-between the recurrent connection. It is with the recurrent connection now. So we have now recurrent connections between the time steps, which account for the dependence between the inputs. So now we are accounting the dependency in between the inputs, and accordingly we are outputting at maybe every time step or at the last time step in different examples. So what is the algorithm to train the network now? Because ultimately the machine learning or any machine learning problem is the training. And here we are training with the backpropagation through time. So how we are going to train? So before proceeding, let us look at the dimension of the parameters because that should be clear. So our input is n-dimensional vector. Okay. Our in-between state, that is SI. SI is at the blue, it is in between state at the blue block. So it is a d-dimensional vector. Yi is the output. It is suppose there are k classes are there. It is a classification problem. Suppose then there are different classes. Then k classes. Suppose then it is a k-dimensional vector. U and V are the weight vectors, and it can be n by d and d by k respectively, and W is on the recurrent line, that is d by d vector. So all these parameters, so dimensions of the parameters, you just look at the dimensions of the parameters here. So how do we train the network? That is the question. So because in between the recurrent connection is there, and therefore the output is depending upon the previous input as well. So that dependency we need to take care. So how to train this particular network? Of course, using backpropagation, but the whatever backpropagation that we are normally applying, that will not be. Some modifications are required in the backpropagation algorithm that we'll see. Suppose our task is of auto completion. That is the first example that we have taken. Predicting the next character. So here I have taken the deep. So at every, whenever I'm pressing D, the next character should be printed, that is E. Whenever next should be displayed E, next should be displayed P, and next should be, next you should stop there after printing deep. So that way the auto completion should happen. So this is auto completion example, how we can use the backpropagation here for this particular example. So for simplicity, we assume that there are only 4 characters in your vocabulary. That is only D, E, P, and stop, because ultimately at the end we have to stop, or at the end we have to give the output at the stop, and therefore there are only 4 characters. This is my vocabulary, and at each time step we want to predict one of these 4 characters. So what is the suitable output function for this particular task? So that is what everybody's answer. Maybe it is a softmax. Okay, so we can use softmax function here to implement this particular thing. And what is the suitable loss function? The suitable output function may be softmax, but what is the suitable loss function? Because we need to calculate loss and we need to backpropagate the losses again through the network. So we can use cross entropy to calculate the losses. So these are the 2 functions we can use at the output side, or whenever we are calculating the output, at that time we will calculate the softmax function. And while calculating the losses, we will use cross entropy. And suppose we initialize initially u, v, w randomly, because initialization is random, and the network predicts the probabilities as shown in the diagram, and the true probabilities are as shown. Again, in green, predicted probabilities are shown, and in red, true probabilities are shown. So we need to answer 2 questions here. So what is the total loss made by the model, and how do we backpropagate this loss and update the parameters? And what are our parameters? U, V, W, B, and C. So how we can update these parameters, or how we can update our network, and how we can calculate the total loss made by the model. Okay, so if you are so outputs are predicted in terms of the you can say probabilities. Fine. So here I am expecting E, therefore 0.7 probability, and your true probability is 1 here. Here also I need E, therefore true probability is 1. Here I need P, therefore here 1 is there, and here I need stop, therefore it is 2 probabilities 1 here. Okay, so okay. Okay, so I think this is wrong actually. Here should be 1, because at the, we need stop is the last one. So here should be 1, that is correct. And no, correct, sorry. Actually this should be 0.7. Okay, 0.7 predicted can be 0.7, but the true probability is 1 here, that is correct. Fine. So true probabilities and predicted probabilities are shown here. And here, while calculating these probabilities, or while calculating these outputs at the output layer, and while calculating the losses at the final layer and at each layer, and how to backpropagate these losses, that also we have to see. So the total loss function, or the total loss, is simply the sum of losses over all the time steps. So at every time step we can compute the loss, and loss can be very easily computed by this particular loss function, log of ytc. Tc means it is yt means it is output at time step t, and c means it is expected classification or expected character out of these 4, because I have only 4 characters and I'm expecting one particular character at every particular time step. So what particular character you are expecting at that particular time step, that is what C is. So this is what the particular loss function we can use. So ytc is predicted probability of a true character at time step t, and capital T is number of time steps, how many time steps you have in the model. So for backpropagation, we need to compute the gradients. So we need to look at how to compute these gradients, and the machine learning is nothing but the computing the gradients only. And once you have the gradients in your hand, what you can do further, you can use any optimization algorithm like gradient descent, and you can calculate the weights. Okay, so gradient with respect to W, U, V, B, C. So all these gradients you need to calculate, and once you have the gradients, everything you can have the gradient descent algorithm to calculate the weights or to decide the parameters. Now let us consider this particular loss function is represented by, or the loss function partial derivative with partial derivative with capital V. Capital V is you're observing here, this is capital V. So with respect to capital V, we'll see we need to calculate the losses at every time step, and we need to calculate the overall loss that is here. And overall loss, the total loss, I can say the summation of the losses, and this particular loss I am computing by calculating the gradients, that means differentiating with respect to one parameter, that is capital V. Okay, so at every time step I am computing and overall loss, but that loss with respect to capital V. So that I'm computing, and each term is a summation. Each term in the summation is simply the derivative of loss with respect to the wet in the output layer. So this is with respect to output layer, that means capital V. Okay, so this is overall loss I'm computing. So let us consider each term in the summation is simply the derivative of the loss with respect to the wet in the output layer, and we have already seen how to do with at the backpropagation algorithm when Vishnu sir has taken the backpropagation algorithm at that time. Already we have seen how to compute this particular thing. Now, with respect to W, because with respect to every parameter, because all these parameters, with respect to all these parameters, you need to compute the loss. So here again, I'm computing the loss with respect to W. So overall loss with respect to W, I am taking like this. It is a summation over all the time step T, but it is here with respect to W. And by the chain of derivatives or derivative rule, we know that this particular can be obtained by summing the gradients along all the paths from that particular loss function to W. Okay, so what are the paths connecting that particular loss function to W? So how many paths will be there? There may be T paths, because here we have T number of networks are there, or T number of stages are there. So here we have 4 paths, and or capital T, we can say it is a capital T. So how many paths will be there? Capital T number of paths will be there. And therefore, L4 theta, that depends upon S4. L4 theta, this particular loss is depending upon this particular state, S4. Okay, so we have dependability, or we have dependency like this. L4 theta, this particular loss is depending upon S4. Further, S4 is depending on S3 and W, previous S3 and W. S3 is depending upon S2 and W. Then S2 is depending upon S1 and W. So this is what the order network that we are getting. So this is what the dependency you are getting. So this particular loss, and this is the overall loss with respect to all the parameters. It is with respect to W and with respect to V as well. So this particular loss depends upon L4 theta at time step 4. This particular depends on S4. S4 depends on, in turn, depends on S3 and W. S3 depends on S2 and W. S2 depends on S1 and W. And S1 is depending upon S0. Okay, S0, that we'll assume S0 is there, right? So where S0 is the constant starting state, some constant starting state. So in order, in an order network, each state variable is computed one at a time in the specified order. So because the arrow you are going, the direction that you are watching from S1 to S2, S2 to S3, S3 to S4, and therefore in an order network, each state variable, that is S1, S2, S3, is computed one at a time in a specified order. That means first S1, then S2, then S3, and so on. And now we have this particular thing. The loss that you are computing. Okay, or the gradient that we are computing, the loss function that we are computing, not the gradient, the loss function that we are computing with respect to W, that is, I am writing as with the chain rule. So this can be written as derivative with respect to S4 and delta S4 with respect to delta W. So this way we can write. So previously we have seen only with respect to W, but this can be written by this way. So we have already seen how to compute loss delta L4 or loss at time step 4 with respect to S4 during the back propagation. In the same way we can calculate, but how to compute the delta S4 with respect to W? It is very easy to calculate delta, because in the same way in the back propagation, whatever way in the back propagation algorithm we are applying to compute the loss function, in the same way we will compute loss function with respect to W, but delta S4 divided by delta W, how we can compute this? That is the question. Okay, so it is a middle state S4, and with respect to W, how we can compute this particular derivative. Okay. So how S4 can be written? So how S4 can be written? S4 can be written in the way, so it is WS3. It is with, as we have written the equations in the previously we have written the equations, in the same way we can write the S4. S4 is equal to some activation function, this is what the wet vector, and S3 is the input to this. What is the input to the S4? S4, it is S3 input plus bias. So in this way we can write this particular S4, and in such an order network we cannot compute the derivative of S4 with respect to W by simply treating S3 as a constant, because it is not actually constant, because it is also depends on W, and therefore we cannot take this as a constant. And in such network the total derivative can be written in two parts. One is explicit part, that means treating all the other inputs as constant, and implicit part, that means summing over all indirect paths from S4 to W. So let us see how to do this. So there are, as I said, there are two parts to compute delta S4 with respect to delta W. So one is explicit part, one is implicit part. Okay, so again this delta S3 by delta W I can write again, because it is again order network, so I can rewrite my delta S3 by delta W as explicit and implicit part. Again I can go ahead and write like this way. Again I can go ahead and write like this way. Okay, so this is what the final thing, and delta S1 is not depending upon anything, and therefore we can stop it here. So I can write these things in this particular manner. So finally, or for simplicity, we will short circuit some of the paths, and we can write like this. So delta S4, we can write this particular thing by adding this, and this is as good as 1. Okay, we can write as it is. This particular second term we can write as it is. Then we will remove these things. We'll short circuit this, and we can write delta S4 by delta S2 and the explicit part. Then we can short circuit this and short circuit this, and we can write delta S4, delta S1, the remaining part. And I can write this as a summation, as an overall general equation. I can write this summation as a general equation like this. From K is varying from 1 to 4, because there are 4 terms. You look at 1, delta S2, delta S3, delta S4. I can write in general delta S4 by W like this. So this is called as, this is finally, we can, actually we are writing we are writing like this. Loss function at time step 4 with respect to W, I can write like this. This particular component is this delta S4 by delta W, and therefore in general I can write my loss function with respect to W as this particular thing and this particular thing here, and this particular delta S4 in general I can write this total thing here. Okay, but as a general. Okay, so by replacing specific like 4, I am writing t, and t is k is variable for this. K is varying from 1 to t, so sk here. So it is varying from 1 to t actually. So this algorithm is called as back propagation through time. So like that way we need to back propagate. So this is very how to compute exactly the loss functions, you can say, and actually these are the gradients actually, because loss function with respect to delta W you are computing. So these are the gradient. Calculation of the gradient, that means calculation of or derivative of loss function with respect to V is very simple, because it is the same like back propagation algorithm, but due to the recurrent connection in between, with respect to W, it is a special case, or this is what the difference here. So you can compute this particular gradient, I can say, or the loss function, derivative of the loss function with respect to W, you can compute this particular gradient like this way. And once you got the gradient, everything is over, because later on you have to apply the optimization algorithm. Okay, so this way we can compute, or we can apply the training, or we can do the training with the help of back propagation through time. Next, I will share my second PPT. So I will share my second, just wait. Okay, now just
Hello, sir. Please share the slide.
yes, I'm sharing it. Just wait. My slide stuck in between. Why so? Wait for 1 minute. Hope it is visible.
Yes, sir.
Okay, fine. So what are LSTMs? Long short-term memories. So what happens here, actually, we said that at every output, we have to consider the inputs or the previous state as well. And therefore, at every time, we are overwriting the state. And as we go on overwriting and the size is fixed, so some of the important information may lose, or we have a short memory, and how to handle the important information in that short memory cell. So this is called as long short-term memory cell. So we have to store in that particular memory location only, or in that memory size only. And the state of the RNN, that is SI, that we have seen here in the blue block, in the middle block, records the information from all previous time steps. Okay, that we have seen. And at each new time step, the old information gets morphed by the current input. Okay, as we go ahead, it is getting morphed by the current input. And once one could imagine that after t steps, suppose the information stored at time step tk minus 1 gets completely morphed. Okay, so suppose if you are at the 20th time step, so the information collected at the 0th time step or the first time step is completely morphed. And therefore, how this problem can be solved? So a similar problem occurs when the information flows backwards, because ultimately we have to backpropagate the errors in the backward direction, right? So at this time also the information get lost. So the similar problems we are facing at the time of backpropagation. So it is very hard to assign the responsibility of the error caused at time step t to the event that occurred at time step t minus k. That means suppose you are assigning the responsibility of the error caused at time step 1 to the event that is caused at time step 20, or the error at 20th time step, and you are assigning the responsibility to time step number 1. Okay, so this is this responsibility is of course in the form of gradients, and we studied the problem in the backpropagation flow of gradients, how we are actually propagating back these particular gradients. So we saw a formal argument for this particular discussion of vanishing gradients. So suppose these gradients are there. So I'm not going mathematically in this particular, because these gradients can be vanished. Because if you see, if you go in detail to the actual length of these gradients, or you can say the parametric length of these gradients. So these gradients may vanish because of some long dependency if you are giving. So if you are giving the dependency of 20th location to the 0th location, or if you are giving the dependency of 100th location to the first location, then these gradients may vanish or exploit. So gradient vanishing problem or exploiting problem, that may occur here as well. And these problems we need to solve. So this can be this actually overwritten part, because I said the states are overwritten, and this particular thing can be this particular thing can be you can compare with the blackboard writing. So we are writing on the blackboard, and we go on writing. So that is marked by the previous content, or that is overridden by the previous content. And only the important thing, how suppose again we want to write something, then some information we are erasing, but the information that we are erasing is not important as per our thinking. That only information only we are erasing, and new information we are writing on the board if you don't have the places. So this particular thing, analogy you can compare with the blackboard writing. So let us look at this particular thing in detail. Suppose you have, that means I have to selectively read, selectively write, and selectively forget something. So what I mean to tell, so that's why we need selective write. Whenever we are writing, we need to write selectively. When at the next time step, whenever we are writing selectively, we should write. Whenever we should read selectively, we should read, and something we need to forget because only we have limited space. So suppose this is a computation problem that we have. So it is AC, BD. Suppose these are the we need to compute this particular equation, AC multiplied by BD plus plus AD. So and board is having only three statements at a time, or this board, whatever board we can have. So this board can accommodate three particular statements at one time, not beyond this. So suppose, in other words, we select what to read actually. Okay. Then at the first time we can write AC is equal to 5. I'm not writing A is equal to 5, C is equal to sorry, A is equal to 1, C is equal to 5. I am writing directly AC is equal to 5 because I have a limited space. Second time I am writing, this is selective write actually. Selectively I am writing. I am not writing A is equal to 1. I am not writing C is equal to 5. Directly I am writing AC is equal to 5 because I have a limited space. So I am writing selective write. AC is equal to 5. Then I am writing BD is equal to 33. So next what I can write? BD plus A is equal to 34. Okay, and these three statements I can accommodate. BD plus A is equal to 34. Next, what to be, beyond this I cannot accommodate, and but my computation is not yet completed. Therefore, what I can do next? I can forget something. Okay, so I can forget BD. Actually, I have included in BD plus A. Therefore, I don't need BD later on, and therefore I can forget that BD. Okay, therefore again space is created. BD I have forgotten. So AC is equal to 5, BD plus A is equal to 34. Again, I can have next particular computation. Again, AC is already included in that computation, and therefore I can forget AC and I can include next computation, and in that way I can go ahead. So this is what selective forget, selective write, selective read. Okay, these are the things happening in this particular example. So this is what the analogy, and with the same, this analogy can be extended to explain the RN. Now, the question is, can we give the concrete example where RNN also needs selective read, write, and forget? And next question is, how do we convert this intuition into mathematical equation, right? So this is what our, you can say, the review problem. So you would like to give the review for the particular paragraph or particular, you can say, okay, paragraph. But at the end of that means at the end, at the last word of the paragraph, you need to give the review. Okay, so consider task of predicting the sentiment. This is what sentiment analysis. You need to say only positive or negative. So RNN reads the document from left to right, all the words, and after every word updates the state. So in between states are given by blue block. So by the time you reach at the end of the document, the information obtained from the first few words is completely lost. Okay, and therefore ideally we want to forget something. So what can be forgetted? Suppose the information added by the stop words, that can be forgetted, that is a, the, etc, like these words can be forgetted. We need to do selective read, the information added by previous sentiment bearing words. So suppose in the previously we have the word, suppose awesome, we have amazing words previously. So we have to retain, or we have to selectively read these words, right? So the information added by the previous sentiment bearing words, that we have to retain. That means that we have to selectively read and selectively write new information from the current word. Suppose we are at the end, suppose, and at the end of the review, suppose there is a word performance. Okay, so that word we need to selectively write, because the new information from the current word to the state that we have to write. So selectively write, selectively read, and selectively forget. These actions are also required in this particular application where the RNN we are applying to solve the problem. Okay, so we need to forget the stop words. We need to select the words uh, which are having the sentiments in that, but in these particular words, and also we need to selectively write. That means new information. Suppose performance, amazing performance. Okay, so performance is the new word. So this information is also you need to write, selectively write to the set. So we need to forget, selective read, and selective write. So selective write, selective read, and selective forget we need in here actually. So now how this can be done in RNN? Okay. Okay. I hope it is visible. Okay. So just to clear, we have computed the state that is the previous state, that is st minus 1, although it is shown in the orange, but it is the state in the blue block actually, the hidden block. So it is the state, previous state, st minus 1 at time step t minus 1, of course. And now we want to overload it with the new information that is coming, that is at time step t, that is xt, that is new information coming, and compute a new state that is st. Compute a new state that is st. How to compute these states? By applying selective write, selective read, and selective forget. That we have to see. So in between, we should have okay. So in between this, so we have the previous state here. So st minus 1 is the previous state. This is the current input we have, and we need to compute the next state. But here we need to apply all three stages, that is selective read, selective write, and selective forget. So as per this particular diagram. Okay. So what is how to selective write? So recall that RNN uses st minus 1 to compute st. Okay. It uses, of course, it uses previous state information to compute st. So here bias is ignored here, just w and u parameters are taken. So this equation already in the previous slides we have seen this equation how to compute st with the help of parameters with the previous state and the current input. So st minus 1 is the previous state and xt is the current input. But now instead of passing this st minus 1 as it to st, we want to pass some selective information to it. We don't want to pass the entire thing. Okay, we don't want to pass entire st minus 1. We want to pass some selected information from st minus 1 to the next. So how we need to select it? So in a strict case, our decisions could be binary. That means some of the information I can take and some of the information I cannot take. That means here multi-dimensional vector is there, multiple values are there. So some values I can take, some values I cannot take. Okay, so for some values I can multiply with 0, for some values I can multiply with 1. And in a strict cases, in a strict decision, few I can say few number of features I can take and other features, some features I will take and other features I will skip, like that way. But a more sensible way of doing this would be to assign a value between 0 to 1 and determine the fraction of current state to pass to the next state. That means instead of being strict, you decide some values in between 0 and 1, you assign, and then you pass some. That means like this. Selective read means, I think with this diagram it will be very clear. Okay, so look at here. So st minus 1, that is the previous state. Ot minus 1, that is how much part or what fraction I need to take. So it is 0.2, it is 0.3 multiplied by minus 0.4, it is 0.9 multiplied by 1. So this is 0.9 means larger part you are taking, 0.29, and ht minus 1. So that means this much information I would like to take, not the total st minus 1. So this is called as, and this ot minus 1, this particular thing is called as ot minus 1, and this is called as the output gate. This is called as a output gate. Okay, so with the help of output gate, I am computing how much information I am going to write to calculate the next particular state. That is a selective write I am doing. I am doing the selective write here. How? With the help of output gate, that is OT minus 1. And gate means what? Here, it is a fractional values. How much amount of the previous state I would like to take to the next state. That is coming in the ht minus 1. That is coming in the ht minus 1. Okay, so I still have my current input. So this is my previous input, but not total. Now I have selective write. I have selectively written something. I have not taken entire thing. I have selected something to write to the next state. That is selective write. Okay, so each element of OT minus 1 gets multiplied with the corresponding element of ST minus 1. That is very clear here. Each element of OT minus 1 is restricted in between 0 and 1. But now, but how to compute OT minus 1? That is the question. How to compute OT minus 1? So how does RNN knows that fraction of the state to pass, what fraction of the state, previous state to pass on? How it will come to know? Okay, so that is what the question is. So whenever you have to find out the parameter. So this is a parameter finding problem, and whenever there is a parameter finding problem, then what exactly you are doing? We are giving some type of training, so that we'll see later. But next we'll see the meaning of selective. Well, RNN has learned, Alan has to learn, because learning should happen. It should learn, because ultimately you need to calculate OT minus 1, that is output gate. So values at the output gate you need to compute. That means you need to learn these values, and here the learning comes again with respect to the parameters. That means you have to find out the parameters W, U, and V. Learning means you need to find out the parameters W, U, and V. Again, you need to find the parameters here based on the previous things. What was important in the previous state, again, that you need to consider, and accordingly you need to decide the values, or accordingly you need to learn the values in OT minus 1. So RNN has to learn OT minus 1 along with the parameters W, U, V. So W, U, V, these are the parameters we need to learn, that we have already seen. But along with that, to learn OT minus 1, some additional parameters you have to learn again, right? So we need to compute OT minus 1 and HT minus 1. So I can write the equations like this way. So OT minus 1 can be, look at the equation of OT minus 1. So these are the new parameters to learn output gate, W0, it is not W. So this is different from WUV. So you are learning the parameters, that is OT minus 1. And so these are the parameters you are learning. Okay, so with these parameters, you are computing OT minus 1. And how you can write HT minus 1? It is a simple multiplication of ST minus 1 and OT minus 1. It is just, I don't think this sigmoidal will come here, because already you have applied sigmoidal at the time of computation of ST minus 1. So it is just a multiplication of ST minus 1 and OT minus 1. Okay, so the parameters, these are the new parameters again. W0, U0 and B0 need to be learned along with the existing parameters WUV. And the sigmoidal function ensures, because this is sigmoidal function ensures the values will remain in between 0 and 1. Okay, so OT is called as output gate, as it decides how to pass to the next time step. Okay, so that will decide how much how much part of the state should be passed on to the next state. This is selective write. Okay, now we'll see the selective read part. Fine. Now we will now use HT minus 1. So this is HT minus 1 computed. Okay, to compute the new state, at the next time step. So this is what the next time step we need to compute everything. Ultimately, finally, we need to compute ST that we have not yet computed. So just we have done the selective write. That this is a current input coming at the time step t. Okay, and we have in our hand ht minus 1. Okay, to compute a new state at the next time step. So how we are going to compute it with the help of selective read. Now we will also use xt because it is the current input at that particular time. So this can be computed. So selectively reading. We are not reading the entire thing. Okay, so this is the input coming, but we are not reading the entire thing. We are selectively reading. We are taking the important information only, and how we are taking the important information depending upon the previous selected uh, information, that is ht minus 1. So here ht minus 1 is the current input, and these are the parameters w, u, and b. So st dash we are computing, not st. This is a temporary calculation, not the final calculation, and that is selective write. And this selective write we are doing on the basis of the computed value ht minus 1, or the computed vector, I can say it is a vector ht minus 1, and the current input xt. We are computing the temporary value, and that is what the selective read is. Still we have not yet computed final st. Okay, still we have to apply selective forget. Okay, so this way we can do selective read with this particular equation. Now s t tilde, that is what the temporary value. Okay, so we have to selectively read. That means again we have to apply some gate and selectively read. So this is what the input, current input at time step t. This is what selectively written information from the previous time step, and on that basis we have computed s tilde, that is temporary calculation. From that selective read we should do. To do the selective read, again we need to compute these values in between 0 and 1, and again we need to, and this is called as an input gate because it is selectively reading, so it is called as input gate, and we need to compute the values of the input gate. So s tilde dash thus captures all informations from the previous state h t minus 1 and the current input xt. So however, we may not want to use all this new information, and that's why we are computing this particular thing, or we are learning. Actually we should learn, or RNN should learn. As RNN should learn this ot minus 1, RNN should learn this it. Okay, and you have to multiply this with s tilde dash temporary calculation. So this is called as input get. This is called as input get. This is input get. Okay, this is input get. So in this way we are selectively reading some information. So IT can be computed with the help of this. Okay, so because IT we need to somehow learn, and as we have written the equation for OT minus 1, similarly we can write the equation for IT. So how to compute the values of IT? How to compute the values of IT, or how the values are related. So with this equation we can find out the learning parameters W, U, and B. So in this way we can learn the values of IT. So IT can be computed by learning. And once you compute the IT with the help of learning, you can compute the selective read part. That means whatever temporary calculation s tilde t that you have computed, so you have to multiply with IT. So you have to compute this. That is called as selective read. That is called as selective read. Okay, so still I have not computed ST. Still I have not computed ST. Okay, this is what the selective read is. So up till now we have these things in your hand. So far we have here. So we have ST minus 1. With the help of ST minus 1, we computed the output gate, OT minus 1. We have done selective write. Okay. After selective write, we computed the temporary value S tilde dash. Then we have got input. So on the basis of this input and S tilde dash, input gate, we have computed the input gate. And on the basis of input gate and this temporary value, selective read we did. So finally we did selective read. Okay. And after selective read, we have to do selective forget. So how do we can combine previous state ST minus 1 and temporary calculated ST tilde to get the new state? Okay. So this is what selective read. This is what selective write. And whatever is the selective read plus the previous state ST minus 1, that becomes ST. Okay, so again, we don't want to take everything from the selective read or selective, whatever selective write that we have done. Okay, so how do we can combine ST minus 1 and S tilde dash? Okay, how do we can combine ST minus 1? So this particular thing, ST minus 1, or this particular thing, ST minus 1, and this particular selective read that we have did, how we can combine this? So again, we can combine this. That means ST can be written. One simple way of ST can be written, whatever previous ST minus 1 and whatever selective read, this is selective read. So total state ST minus 1 previous state plus selective read. Okay, plus selective read. That way we can write ST, but this is not actually actual thing. We need to forget the information which is unimportant, that we need to forget, and we have to apply the forget gate here. And finally, we can say we can write like this. Okay. This is selective forget. So I think this is clear. This is clear. To selective forget, whatever ST minus 1 is there. So from that we need to forget something. Okay, from that we need to forget something, and to forget something again we need to compute the forget gate. Right? So selective forget state is applied here, and after applying the selective forget, that means on ST minus 1 you are applying FT, that is forget gate, and you are computing the new thing, and whatever selective read plus whatever this newly calculated value, this you are adding, and finally you are computing the ST. And therefore ST can be written as now like this. First, how to compute the FT? FT can be computed with the help of, see the equation, HT minus 1. It is computed with the help of HT minus 1. It is with the help of XT and some bias values. So FT can be computed, and this FT is applied. This FT is applied on ST minus 1. ST minus 1. Okay, and accordingly this is calculated. So this is ST. So this is ST now. So we now have the full set of equations for LSTMs, that is ST and OT. Okay, and in the this OT is nothing but this is for the next layer. This OT, this is for the previous layer. Okay, so what are the computations are happening in the current time step? Because there are two time steps here, T minus 1 and T. So what are the computations are happening in the current time step? I can say these are the computations are happening, because wherever T is occurring, these are the computations are happening in the current time step. So this computation is happening, this computation is happening, this is at the previous time step, fine. This is. So 6 computations are happening at the current time step. So this way you have to compute, or this way you have to compute the next state. So we now have full set of equations of LSTM. You can So all these gates, because we need to compute all these gates first. So how to compute all these gates? These are the equations for computing all these gates, and we need to compute states as well. So at time step t, so these are the calculations, 6 calculations for gate calculations, these 3 calculations for state calculation, in between state calculation. Finally, you are getting ST. Okay. For state calculations, we have to apply these 3 equations. So 3 plus 3. So at particular time step t, this much is the calculation in LSTM. Okay. So this is actually how actually the LSTM works. So this is what the explanation is with the help of selective write, selective read, and selective forget. I would like to show one demo here as well. Is this clear to you? Any questions? Quickly, we will go through one demo.
Okay, sir.
Okay, so this is self prediction example. Just wait, I will share them. Yeah, I will share. I think it is visible.
Yes, sir, visible.
Okay, so these are some of the important libraries that you need to import. I'm not going into detail because I think we have only 2-3 minutes left. Okay, or you can go on Kaggle and you can access this particular code. The explanation is there as well. Just here, LSTM is imported here from TensorFlow.keras .layers import LSTM, and you have some time series data. That is very important. So you have some time series data, and what is my problem is? My problem is to predict the next time step data. Okay, and depending upon the previous 3 steps. Okay, end steps means how many input data you are considering to compute the next time step. So suppose this is first 2, 3, 4, 5, 6, 7, 8, 9. So at 10th time step, these 3 values you will consider to compute the next time step. When you got this, 11th time step value can be computed with these 2 value and predicted value. Like that way, it will go ahead. And to arrange your data or to prepare your data, this is what the function written. So it will write the function, it will prepare your data like this way. So you have one 110, 125, 133. Okay, 110, 125, 123, 125, 133, 146. Like that way, 3 values are collected: 125, 133, 146, and like that. And this is the output. So this is for this particular input: 110, 125, 133, 146 is the input. 146 is the output. Like that way, you X and Y value, that means input and output values are prepared. So this is the function for preparing, this particular is the function for preparing X and Y. So your input and output values are prepared, and just you have called the model, or just you have added the model LSTM, okay, with activation function ReLU, okay, with the 50 input neurons in the hidden layer, okay, as we have seen in the CNN case, and somewhat some optimizer we have applied, and this is what a fitting with the value. So once I have fitted the function, okay, so I'm not executing it now. Already I have executed it here. So just output after learning, after executing or after fitting the function, what I am doing, I am calculating the values. So first value I need is what? First value I need is 10th value. 10th value means, and I will compute the 10th value on 187, 196 and 210. Once I got the 10th value, I will use 196, 210 and that particular 10th value to predict the 11th value, like that way. So here the code is written like that way. So if else part, in the else part, the first, the last three values are taken and the 10th value is computed, and in the if part, the further values are computed. So this is what the computation of the 10th value. I'm directly showing it here, 10th value. Next, what is the input for the day one? Suppose it is sales data, and what is the calculation? So when you take the previous two, this is the 10th value, newly computed value. These are the previous values. On the basis of that, the first day means 11th day. Actually, it is a first prediction, 11th day calculation I am doing. Then whatever this new value, that will come here. Previous two values will come here, and the next value is calculated like that way, and it will be done for the next few days. So this can be done because as this is a series, as this is a problem of sequential data, you can apply RNN here. Also, another example can be shown here, that is predicting the next character or predicting the next text. So here, that particular code is here. Here also RNN is applied. So starting sequence is given, okay, and you need to give the generator.
No, sir. That code is not visible.
Code is not visible. Yes, I should share. Okay.
Okay, sir.
So I'm loading some text first, and that text I am taking from some website, okay, and some pre-processing I am doing on the text with the help of tokenizer and all these things to differentiate between the to separate out the words with the help of tokenizer. And sequences, I am giving the input as a sequences. So create input sequences. This is one function is there. So what exactly important is here? Build LSTM model for it. So it is a sequential model, okay, with LSTM with 100 you can say 100 neurons in between, or a hidden layer with the 100 neurons, whatever blue network that I have shown there. So that is with the hidden network with 100 neurons. And finally, I am fitting that particular model here. Okay, train the model here. And after training, suppose if you are giving any seed text, suppose you are inputting, then auto completion, it is doing the auto completion. It is doing the auto completion depending upon the sequences that it has sequences that has occurred in between the text that you have provided. So it is learning on this particular sequences that are occurring in this particular text that you are providing. It will learn the understands the sequences there, and if you uh, give the input, it will give the further output. Okay, so enter the seed text. I have given C saw, that is what my seed text. Okay, and if you go to that text, it is a very big paragraph, or it is a very good, very big document is there. So just I given seesaw, so it is giving further seesaw, the queen, and the other was all the something like, I mean, it is predicting the next characters or next words depending upon the sequences that it has got in the given report or given paragraph. So in this way, you can use the RNN for exactly predicting the next particular sequence or next particular word or next particular value in the case of cells prediction, in the case of word prediction, or any sequential data that you can say. Your voice is a sequential data. Your video is also sequential data. What may be the next frame that you can compute with the help of the previous frames. Okay, so whenever there is a sequential data, you can learn the important things in the sequences with the help of selective write first, then selective read and selective forget, and you can compute the next state. In that way, at every time step or in the last time step, you can give the output with the help of RNN. So I think we'll stop here. So anybody is having questions, then we'll take. Otherwise, we'll stop.
Anybody having questions?
No, sir.
Okay, sir. Okay, so thank you, sir. Okay, for your nice presentation. You have explained the recurrent neural network as well as sequence modeling. Okay, also you have explained sequence learning problem, recurrent neural network, backpropagation through time. Okay, with the help of simple diagrams. Okay, so that anybody can easily understand. Okay, also you have explained the concept of selective read, selective write, selective forget. Okay, with the help of very simple explanation. And the important part was the last. Okay, you have explained the the concept of number prediction and text prediction with the help of recurrent neural network. Okay. So thank you for your explanation and the demo also. Thank you, sir.
Okay, we'll stop here.
Okay.
Thank you.